Hello students, welcome to the chapter 4 lesson 9. So in this lesson we will see the applications of the column analogy method to symmetric total frames. We'll do a problem related to this. So far we have done problems on beams using the column analogy method. So now we'll see a symmetric total frame. Right. Now this is the problem given to us. So AB and CD is are columns and BC is a beam. On BC you have a 120 kilonewton load at 2 meters from C. For all the three members, moment of inertia is I. The column lengths are 4 meters and the beam length is 8 meters. Right. So we have to analyze the frame and draw the bending moment diagram. Right. Now before getting into the problem, see this is a indeterminate structure frame. Right. We have to make a basic determinate structure. Now how can we make a basic determinate structure is, there are two fixities here. So let us consider this as hinge and let us consider this as roller to get our what? BDS. That's your basic determinate structure. Okay, so A point we have considered as a hinge and B point we have considered as a roller to get the basic determinate structure. Now, what is the free bending moment? Free bending moment is nothing but whatever is the loading for that. Because of that, whatever bending moment we get, that is your free bending moment. So, free bending moment will come only on the span BC. Now, what is the value for that? It is eccentric point load. So, WAB by L is the maximum free bending moment we will have on the span BC. So, let's do the substitution. W is how much? 120 kilonewton. Now, A is, so this total is 8 meters. So, this will be 6 meters. So, this is your A and this is your B. Right. So, there will be 6 into 2 by 8. So, this will give us a value of 180 kilonewton meter. So, this is the free bending moment. Now, if you want to draw the analogous column, how will we draw? Now, see the length will not change. I is same for all the three members. So, how will your analogous column look? Now, on the analogous column, we have to draw the bending moment. So, I'll first draw the analogous column. Right. Now, if you observe, it's I, and I. So, the width will be I here. The width will be I here. And the width will be I over here also. Right. So, what is this? This is I by 1 by EI, you can say. Here, this is also 1 by EI. And this portion is also 1 by EI. Okay. And how about the length? The length here is 8 meters. The length here is 4 meters. And the length over here is also 4 meters. Now, where will the CG of this come? So, if you try to draw it, so the CG will come somewhere here, which we have to calculate. Let me name it as G. Okay. So this is what point A, this is point B, this is point C, and this is point D. So this is your analogous column. So on the analogous column, what we have? We have the free bending moment. So let me draw the free bending moment here like this. So wherever the point load is there, there you will have the maximum bending moment, and how much is that value? 180 kilonewton meter. So on this analogous column, we have a loading, triangular loading with maximum at under the point load. Okay. So this is the, so let me name it. So this is your analogous column and this is your MS by EI diagram. Got it? So on the analogous column, whatever loading is there, that we have put, so that is your MS by EI diagram. Now what we have to do is we have to find the properties of our analogous column. So what did we do initially? We took the basic determinate structure, calculated whatever is the free bending moment, drew the analogous column, and on the analogous column we have put the bending moment by EI diagram, right? So we have created the analogous column in our first step, right? Now what we'll do, we'll try to find all the properties of the analogous column. So analogous column properties, right? Now first let us find the area of the analogous column. I am calling it as A. There are three portions, right? So these two portions, what is the width? 1 by EA is the width. Depth is what? 4. Right, like that we have two columns. Here one column and here one column. So into 2 we can do. Plus this one is what? 1 by EI into 8. Right, so totally we get what? 8 plus 8. 16 by EI is the area of this analogous column. Now if you observe, symmetric axis is nothing but the principal axis YY. So this is what your symmetric axis. So let us call this as XX. So symmetric axis is the principal axis YY. Now to locate the centroidal axis, what we have to do? Centroidal axis X, what we have to do? The moment of the area about the beam BC we have to take and then divide it by the total area to get the centroidal axis. So I'll call this centroidal axis as YC. What we have to do? The moment of this entire area about BC. We're taking it about BC and dividing it by the total area, we get the YC. Okay, so if I want to write, so this is area, now we are doing the centroidal axis. YC will be what? A1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. This is nothing but your a1 plus a2 plus a3. Right. So what is a1? 1 by ei into 4 is the a1. Now what is y? y1? y1 is the distance between this portion and this portion. So this is 2. Right. Similarly, plus A2 is what? 1 by EI into 8. So let me call this as first portion, this as second portion, and this as third portion. So this is your A2. Y2 is what? The centroid of this and the BC line is at the same point. So that will be what? 0. So coming to the third one, again it's what? 1 by EI into 4. Again the distance is how much? 2. Okay, so this will anyways become 0. This has to be divided by 16 by EI to get the value of your YC. So if you simplify, you will get your YC as 1 meter. Right. So once this is done, what we have to do? We have to do the CG of the, we have to plot the CG. So the CG is plotted here. That's nothing but your, so this is your YC. This portion is your YC. So this is how much? 1 meter. So the remaining this side is how much? 3 meters. Right. Now once this is done, we have to calculate the moment of inertia about XX as well as YY. So for IXX, what is the general formula? Parallel axis theorem formula, BD cube by 12 plus AH square is the parallel axis theorem formula. So we are doing IXX first. So the B is 1 by EI. We'll do one thing, 1 by EI totally I'll take common. Right, so it will be what? BD cube by 12. 1 into D cube by 12. Right. plus AH square. A is 4 here. H is what? The distance between the CG of this and the centroidal axis. So here it is how much? Total is 2, 2 minus 1. For this particular AB and CD, the CG is at 2 meters, but our CG is at 1 meter. So the difference is what? 2 minus 1. That is your H. Okay. So into, square. Right. Now this is for what? This is for this column. So similarly, it is for CD also. So this can be multiplied by 2. Okay. For AB and CD, both it is same. So I have multiplied it by 2. Now this along with for the portion BC. Okay. AHQ, we have to just do AH square. So area is this and H is how much? 1 square. So on simplification, you will get the value of your IXX, that's 26.667 by EI. Similarly, do it for your YY. Now, for these two column portion, we'll just do AH square. So that's your 1 by EI into 4 square. Right, this has to be done for both the columns, so multiply it by 2 plus BD cube by 12. So BD cube by 12 for the BC portion. So on simplification, you will get your YY also, which is 170.667 by EI. So here 1 by EI is too small. That's why what we are doing is 1 by EI whole cube also if we get, we are neglecting it. Okay. So wherever here in both the places we got 1 by EI whole cube, we have neglected it. That's why I have not written the extra portions. Understood? So this is your IXX and IYY. Now after this, the step 3, what we have to do is find the properties of the load diagram. Okay. So whatever is the loading diagram, that properties we need to find next. So step 3 is to find the properties of load diagram. Now, first is what? Let us find the total load. Okay, total load P. Nothing but what is the total load? Is the area of MS by EI diagram. So half into base into height. Half base is 8 meters for this, and height is how much? 180 by EI. Right, so that will give us 720 by EI. That's the area of the load diagram. Now once that is done, the CG, where is the CG of the load we need to find? We'll find it from point B, that is from this point. Let us find where is the CG of this. So for unsymmetrical triangle, what is it? L plus A by 3, because we are coming from this side, we have to take L plus A by 3. If you are coming from this side, we have to take L plus B by 3. Okay, so this is L is how much? 8 plus A is how much? 6 meters by 3. That's nothing but your 4.667 meters. Right, now once this is done, we have to find EYY, MYY, EXX and MXX. So eccentricity in YY direction and eccentricity in XX direction. Right, so in YY, what is the value? It is 4.667 like this, minus the center will be 4 meters. Right, so this will be 0.667 meters, and it is towards what? It is towards 0.667 meters towards C. So based on this, what is your My? My will be load into your eccentricity. So what is the load? 720 by EI into the eccentricity 0.667. So this will come up to how much? 480 by EI. Similarly, EYY will be directly 1 meter. So we don't have to do. So this whatever YC we have got, that is your EXX. Okay. So that will give you a moment equal to what? P into, so this is what? P into EX or this value. So P is 720 by EI into X is what? 1. So that will be 720 by EI. So this will cause what? Compression in the right half portion. Compression in the right half portion, and this will cause what? Compression in above XX portion. So this will cause in the right half portion and this will cause in the above portion. Okay. Now after this, what we have to finally do is, once we get the MXX and MYY, we have to find the moment of this loading diagram about every point, that is about A, B, C and D. Okay, so let's do it here. MIA, I call it as MIA, and here let me call it as MIB. Okay, so how will we do that? So 720 by EI into EI by 16 for the portion 1, then 480 by EI into EI by 170.667 into 4 for the portion 2, and minus 720 by EI into EI by 2667 into 3 for the portion 3. Okay, so this will give you a value equal to 45 minus 11.25 minus 81. So this will give up to value of minus 47.25 kilonewton meter. Right. Now similarly for MID, everything will remain same. 45, instead of minus it will be plus 11.25 minus 81. So this will give you a value equal to what? Minus 24.75 kilonewton meter. Now for IB, it is everything is same other than this value where it will, the distance will change. Okay, so it's 720 by EI into EI by 16 minus 480 by EI into EI by 170.667 into 4. And finally, it will be minus 720 by EI into EI by 26.667 into, instead of 3, 1 will come. That's the only difference. So we'll get 45 minus 11.25 plus 27, which will give you a value equal to 60.75 kilonewton meter. So your MIC will be same 45, but here it will be plus 11.25 plus 27. That will be 83.25. So these are your moments at the 4 points of the frame. Okay. Now the final step is to find the final moments. So step 4 is finding the final moments, for which the formula if we want MA to be MSA minus MIA. Okay, so that's 0 minus of minus 47.5, that's 47.5 kilonewton meter. So this is SA's way, but this is a symmetric frame, so this will not come into this. For everywhere it will be 0. Okay, and MB again it will be what? 0 minus 60.75, that's minus 60.75 kilonewton meter. Then your MC again 0 minus 83.25, that's minus 83.25 kilonewton meter. Finally your MD, that's 0 minus of minus 24.75. These are the values which we have previously found now. Okay, so that will be what? Minus plus 24.75 kilonewton meter. Okay, now what we have to do? These are your final movements. You just have to draw the bending moment diagram. Very simple, very simple. So take the frame, plot the values. So how much is this? 47.5. 47.5. Okay, negative will take it here. So this is 60.75. Here also it is 60.75. So both this is 60.75. 60.75. Here is how much? 83. So let's go a little above 83, and this is how much? 86. So 83.25. This is 83.25. Here is how much? 24. Okay. So this is 24.25. This was 47.5. Now we just have to join this using a straight line. So this is a linear line. Okay. So these are because of the final end moments. Right, now along with this, the free bending moment diagram should also come. There's only loading at this plan BC. We got it how much? As 180, right? So 180 will go somewhere on top. Here, this is a linear line. So this portion will be 180 kilonewton meter. So all these units are kilonewton meter. So what is this? This is your final bending moment diagram. So they have asked you to analyze the frame. Analyze is finding the final moments, and then they have asked you to draw the bending moment diagram. So this is how you have to do if asked for the symmetric frames using your column analogy method. So in the next lesson, we'll see how to do it for closed rectangular frames.